Announcements. Some basic announcements. The first homework for chapter 3 is due on the 7th. That's Monday next week. The second homework will be due on the 14th. That's the Monday afterwards. The quiz for chapter 3 will be on the 14th. And so we have one person here, Yessie Cruz. Okay. So that's announcements. I'm still working on grading the tests, so they're not done yet. They will be done eventually. So, quick review of Newton's first law. An object will remain at rest or in uniform motion in a straight line unless it's acted on by an external name. Williams. Unless it's acted on by an external unbalanced force. Balanced forces have equal magnitudes in opposite directions, and an external force is a force applied to the entire object or system from outside. So if you have an asteroid traveling at 30,000 kilometers per second, if it's not affected by external forces, what will its speed be in 2 years? This is very simple. No external forces, so it'll remain in motion in a straight line at a constant velocity. So it'll still be 30,000 kilometers per second. It's kind of tricky to write for first law questions because it's about nothing happening. So let's move on to Newton's second law. Newton's second law of motion is that force equals mass times acceleration. Okay. So it's the relationship between acceleration, force, and mass. So if you start testing various objects based on how much acceleration they gain, depending on their force and their mass, you'll find that acceleration is proportional to force over mass. So the bigger the force, the bigger the acceleration, the bigger the mass, the smaller the acceleration. It's directly proportional to the magnitude of the force and inversely proportional to the mass of the object. And it turns out we defined our units of force such that acceleration equals force divided by mass, or force equals mass times acceleration. That's how we've defined our units. Or the third way you can write this is mass is force divided by acceleration. You can, in theory, measure mass that way. So, for example, acceleration is proportional to force over mass. So if we have a force, if we double the force, we get double the acceleration. However, if instead we use the same force we started with up here, but we double the mass, we'll get half the acceleration. So acceleration is force over mass, or force equals mass times acceleration. Those are the same equation. If we double the force, we double the acceleration. If we double the mass, we halve the acceleration. So force is in units of newtons. 1 Newton is 1 kilogram meter per second squared. Force is the net force. It's the total force on the object. Which is likely the sum of 2 or more forces. Mass and acceleration are concerning the whole system. And the units, force is mass times acceleration, so it's kilograms times meters per second squared, which gives you newtons. 1 Newton is 1 kilogram meter per second squared. This is the derived unit for force. And we don't want to write kilogram meter per second squared over and over again, so we call it a Newton. From this point on, when we start introducing new units, they will generally have names. So in the next chapter, we're going to introduce energy. Energy is measured in joules, which is kilogram meters squared per second squared. But yeah. So here's an example of the total force and the total mass. So if you have a system of objects, you can do the total force equals the total mass divided by the acceleration of the system. So we have two blocks that are connected together, so we can treat them like one big block with the total mass of the sum of them, mass 1 plus mass 2. Each block weighs 1 kilogram, so the total mass is 1 kilogram plus 1 kilogram, 2 kilograms. And our force, we have force 1, which is to the left, so it's negative. We have negative 5 newtons to the left. And force 2, which is to the right, so it's positive 8 newtons to the right. And so if we combine the forces to get the total force will be negative 5 plus 8, which is 3. And so if we want acceleration will be negative 5 plus 8 divided by, well, here, I'll just show you. So mass 1 is 1 kilogram, mass 2 is 1 kilogram. The net force is going to be the sum of the forces. Force 1 is negative 5 newtons, force 2 is 8 newtons. So 8 newtons plus minus 5 newtons, that's going to be 3 newtons. Divided by 1 kilogram plus 1 kilogram, that's going to be 2 kilograms. 3 newtons divided by 2 kilograms is 1.5 meters per second squared. So if you have a 10 kilogram block on a frictionless surface, that means you don't have to worry about friction forces. It's being pushed to the left with a 200 Newton force. What is its acceleration? So it's experiencing 200 newtons of force to the left. And it has a mass of 10 kilograms, and we want to find acceleration. Yes, it is 20 meters per second squared. So force equals mass times acceleration. If we want to find acceleration equals force over mass. You know? So acceleration equals force over mass. Our force is 200 newtons. Our mass is 10 kilograms. 200 newtons divided by 10 kilograms is 20 meters per second squared. Now, well, any questions about that? Everybody got that? If you have a 20 kilogram mass that accelerates at 28.8 meters per second squared, what is the net force on that mass? Remember, force equals mass times acceleration. Yes, that is correct. Just needed to check. So it's 576 newtons. Force equals mass times acceleration. So 20 kilograms times 28.8 meters per second squared gives us 576 newtons. What? Sorry. Well, so those are the same. Force is mass times acceleration, and you can rearrange that equation to acceleration equals force over mass. These are the same equation. Just it's often used. A lot of people have trouble with algebraic manipulation, so I've given you both. This is sort of how you derive it and think about it, because acceleration is, you get more acceleration when you have more force and less when you have more mass. But this is the way it's most commonly written, because it's all one line. So here you have a cart pulled by 1,440 Newton force that accelerates at 12 meters per second squared. What is its mass? So just as a reminder, the last way you can rearrange this equation is that mass equals force over acceleration. And all of these are the same equation. This Newton, where here in the problem? Here, you mean? That's newtons, the unit for force. So 1 Newton is 1 kilogram meter per second squared. So we will be measuring force in newtons. If we were in the imperial system, the unit for force is pounds. Yes. 120 kilograms is correct. The force equals mass times acceleration. If we want to find mass, we can divide both sides by acceleration and get mass equals force times divided by acceleration. So 140, well, sorry, 1,440 newtons divided by 12 meters per second squared gives you 120 kilograms. So here, if we have, this is combining this stuff with stuff from last chapter. If a 30 Newton force is placed on a mass starting at rest, and after 3 seconds, the mass achieves a velocity of 9 meters per second, what was the mass of this object? So here you're going to need to use the fact that acceleration is final velocity minus initial velocity over time, and that force equals mass times acceleration. There's 2 steps. And you'll be able to find the mass. Yes, it is 10 kilograms. So the first step is to find the acceleration. Acceleration is final velocity minus initial velocity over time. Our final velocity is 9 meters per second. Our initial velocity is 0 because we started at rest. The time was 3 seconds. So 9 meters per second minus 0 divided by 3 seconds gives us an acceleration of 3 meters per second squared. So now that we know acceleration, we can then find mass. Force equals mass times acceleration. And thus mass equals force divided by acceleration. So mass will be the force, 30 newtons, divided by the acceleration, 3 meters per second squared, which is 10.0 kilograms. So we start by finding out the acceleration from the motion information, and then we use the acceleration to find what we're looking for with Newton's second law. Now, a special case of Newton's second law is the force from gravity. Everything, when we drop it, accelerates at 9.8 meters per second squared. Well, that's an acceleration. There must be an associated force. So weight, the weight of an object, weight equals mass times the acceleration due to gravity. So on Earth's surface, this is a special case of F equals ma. The weight of any object is its mass times g, the acceleration due to gravity. Because the force of gravity, it turns out, is proportional to your mass. So the more massive you are, the more force you have. And we'll get to that when we cover the general equation for gravity, which we'll do a little later in this chapter. Basically, if you double the mass of an object, that would normally cut its acceleration in half, but it also doubles the force because the force of gravity is proportional to the mass. And so the acceleration stays the same. So your weight changes due to the changing, your weight can change due to the changing pull of gravity. So if you go somewhere where the acceleration of gravity is less, like if you want a trivial amount, you go up an elevator to a very top of a very tall building. and your gravity will be ever so smaller, or your weight will be ever so slightly less. If you want a bigger change that's reasonable on Earth, well, when you get in an airplane, you're up quite high. Or if you go to the equator, the acceleration due to gravity is lower at the equator. But if you want a dramatic change, if you went to the moon, the acceleration due to gravity is only a sixth of that on Earth. So if your weight on Earth was 300 pounds, on the moon, your weight would be 50 pounds. So here we can calculate what the weight of a 2.45 kilogram mass is on Earth and on the moon. Well, our equation for weight is mass times gravity. So mg, so our mass, 2.45 kilograms times 9.8 meters per second squared, gives us 24 newtons. 2.45 times 9.8 gives you 24 newtons, or about 5.4 pounds. On the moon, G is 1/6 of what it is on Earth. So basically, we just divide 9.8 by 6, and you'll get 4 newtons. You'll get a sixth of what you would get on Earth, which is around 0.9 pounds. And the acceleration due to gravity is independent of the mass, because when you increase the mass of an object, say if you double the mass of an object, you tie two textbooks together, both the force and the mass get doubled, leaving the acceleration the same. So if you multiply the top and the bottom by 2, nothing changes. And that's what's happening with gravity. So here a 10 kilogram mass is dropped and it's only affected by gravity. It accelerates at 9.8 meters per second squared. How much force does gravity place on the mass? Yep. So force is mass times acceleration. Weight is mass times g. So 10 kilograms times 9.8 meters per second squared, 98 newtons. And if you want a rough approximation, 100 grams is about 1 newton. So here we have a helicopter. It's accelerating upwards. So its total force up is pointing up. And it has a mass of 4 times 10 to the 6 kilograms, and it's accelerating upwards at 3.5 meters per second squared. How much force must the rotors produce in order to counteract gravity in this way? So just a quick diagram of the forces here. There's some force from the rotors. There is the weight pulling down, and the force from the rotors minus the weight equals the net force which is going to be the mass times the acceleration. And it's minus the weight because the weight is down in the negative direction while the force of the rotors is up. So the net force is the force of the rotors minus the weight, which is mass times acceleration. So the question is, how much force are the rotors generating in order to counteract gravity this way? And the mass of the helicopter is 4 times 10 to the 6 kilograms. G is 9.8 meters per second squared. So net force equals mass times acceleration. The net force also equals the force of the rotors minus the weight. Because the net force is just the sum of the forces. The forces are the force of the rotors up and the weight pulling down. And that equals mass times acceleration. So the force of the rotors is going to be mass times acceleration plus the weight. Because we're just adding weight to both sides. But the weight is mass times g. So here we can then plug in numbers. So we have 4 times 10 to the 6 times 3.5 meters per second squared, which is going to be 14 million, plus 4 times 10 to the 6 times 9.8 meters per second squared, which is 39.2 million. So 1.4 times 10 to the 7 plus 3.92 times 10 to the 7 newtons, which adds up to 5.32 times 10 to the 7 newtons, or 53,200,000. If you wrote it out as a big number. Don't we? No. Sorry. I was just checking if I had it written out as a number. But this is 5, 3, 2, 0. So 53,200,000. Put in the comments. And this is effectively the mass times G plus A. Now, friction is a very common force. We use friction every day. I am in fact utilizing friction right now to walk around the room. Because friction is what transmits force between me and the ground and allows me to move. So friction is the resistance to relative motion that occurs whenever two materials are in contact with each other. And there's always friction. It's pretty much impossible to eliminate friction. So you find types of various forms of friction in all states, solids, liquids, gases, whatever. Now, sometimes we want friction to happen. Like in the winter, we would like our roads to have more friction rather than less friction. So we put sand on ice to increase the amount of friction that the roads have. In other cases, we want to reduce friction. So we'll lubricate parts we don't want to rub together and wear out with things like motor oil. So yeah, sometimes you want friction, sometimes you don't. When I'm walking around the room, I want friction between my feet. But at other times I won't. Other things, I don't want friction in my joints. And there's two types of friction. There's static friction. Static friction is what keeps things from moving relative to each other. So static friction is what makes it hard to get something moving. It's also what you use to walk around with your shoes, because my shoes are not moving relative to the ground when I'm walking. Similarly, it's what actually we use to drive. It's static friction between the tire and the road that makes the car go forward. The point of contact between the tire and the road in a car isn't moving relative to the road. And if it does move, that's when you skid out or burn rubber. And that's less efficient. Now, so static friction is the friction force that is trying to keep things from moving. There's also kinetic friction, is when things are moving and it's trying to stop the motion. So static friction is as strong as it needs to be to keep something from moving up to a maximum. Kinetic friction is just as strong as it's going to be, and it occurs between two surfaces that are already moving. But in general, static friction is stronger than kinetic friction, which is that maximum for static friction is higher than the kinetic friction, which is when you lose grip on your tires, you don't get moving as well, for example. Or, no, it's harder to propel yourself if things are slippery, kind of thing. So in general, once you start sliding, you don't get as much force. You don't get as much friction. Also, it is harder to get something started moving than to keep it moving. You may have noticed that if you're pushing a big heavy box or something like that, once it gets going, it's easier to keep it going than to get it started. So usually it takes less force to keep something moving than to start it moving. And so a lot of the times in things like your car, you would like to have static friction rather than kinetic friction. You'd like to have static friction between your wheels and the road. That's the normal case. And if you don't, that's when you're doing like a burnout or you're skidding, and that's bad. You have less control. And the strength of a friction between two surfaces is described by the coefficient of friction. These are dimensionless quantities that are used to characterize particular contact situations. So they depend on the two materials that are in contact with each other. And both coefficients of static friction and coefficients of kinetic friction, they're measured experimentally for a wide range of contact surfaces. And in general, the coefficient of static friction is greater than the coefficient of kinetic friction. So here are some examples. So for example, with aluminum on aluminum, Static friction has a coefficient of 1.9, kinetic is 1.4. Aluminum on steel, static is 1.61, kinetic is 0.47. Steel on steel, if it's dry, is 0.75, 0.48, but if it's lubricated, it can be as low as 0.12 and 0.07. That's why it's useful to lubricate joints. And then Teflon on steel is 0.04 and 0.04. Teflon's super slippery. And Teflon on Teflon is similarly about 0.04 and 0.04. Teflon is the stuff if you're going to encounter on a day-to-day basis that's got the lowest friction. There are actually things that are lower. For example, here, lubricated ball bearings is lower. Your joints, your synovial joints, the connections between them are lubricated and made of cartilage, and that's actually lower as well. Rubber on concrete, on the other hand, is quite high. If it's dry, it's about 1.2 and 0.85, but it is significantly reduced when it's wet, 0.8 and 0.6. Wood on wood is about 0.58 and 0.4, and then lubricated ball bearings is less than 0.01. That's got a number of ways that it reduces friction. So, that's why we use ball bearings for things that need to spin forever. So, in general, we're not going to deal with the coefficients of friction and the formula for that. Just be aware of them. But I might have a problem where I mention friction as a drag force. So if friction provides a drag force of 20 newtons for a 30-kilogram cart, how much force must I apply to get an acceleration of 5 meters per second squared? So this means that if I apply a certain amount of force in the positive direction, there's going to be a negative drag force of 20 newtons. So I'll have whatever force I apply, I'll have some drag force of 20 newtons that I'll have to overcome to get my desired acceleration. No. So the net force will equal mass times acceleration. But in this case, the net force is going to be the applied force minus the force of friction. Because that drag force is going to be in opposite the direction of the acceleration. So it's going to be negative. So if we want to figure out the applied force, it's going to be mass times acceleration plus our friction force. So our mass is 30 kilograms. Our acceleration is 5 meters per second squared. So we're going to have a net force of 150 newtons. And then we're going to add the 20 newtons of friction because we have to overcome that as well. So we need 150 newtons to get the cart moving at the desired acceleration, plus another 20 to get rid of the friction. So we'll need a total of 170 newtons. If you wanted to keep this cart going at a constant velocity, you'd have to just counteract the drag force. And so your net force would be 20 newtons positive. So that's the force that you have to apply to keep something going at a constant speed. That is just overcoming friction and drag. Everybody got this? Okay. So here we have a block being pushed across the floor at a constant speed of 4.5 meters per second by a horizontal force of 490 newtons. So this situation is something like, because the speed is constant, we have a block, it has some force applied, and some force of friction, and force applied minus friction equals 0. They're the same size. So this is going to be 490 newtons, and the friction is going to be 490 newtons. So if the block stops, will 490 newtons be likely to start it moving again? Yes or no? So when it's sliding, you need 490 newtons to keep it moving. If it comes to a stop, would 490 newtons be enough to get it started moving? Nope, that is correct. It would not, because to get it started, you have to overcome static friction, and static friction is usually stronger than kinetic friction. So the kinetic friction was 490 newtons, which means that the static friction is probably going to be more than that. Can't tell you how much more, because it depends on the surfaces, but it's likely to be more. I don't know of any material where static friction is less than kinetic friction. I know some where they're basically the same, but not less. So that was Newton's second law and friction. So let's talk about Newton's third law of motion. Newton's third law of motion is about how forces occur. Newton's third law says forces don't happen on their own. Every force involves two things interacting with each other, and they either pull on each other or push on each other with the same amount of force in opposite directions. So what that says, for every action, there is an equal and opposite reaction. So what that means is, if I push on the wall with 20 newtons of force, the wall pushes back on me with 20 newtons of force. So whenever an object exerts a force on a second object, that second object exerts an equal and opposite force on the first object. So action equals opposite reaction. So force 1 equals minus force 2. So the force on 1 equals minus the force on 1 equals minus the force on object 1 equals minus the force on object 2. if the only forces involved are the two forces interacting, which means that mass 1 times acceleration 1 will equal minus mass 2 times acceleration 2. So this is for things like two things being flung apart by a string, two things being pulled together by a rope, things like that. And you can think about it as the force of 1 on 2 equals minus the force of 2 on 1. That's how I like to think about it. Or you can write it as force of 1 from 2 and force of 2 from 1, either one. But the general idea is that if you push on something, it pushes back on you with equal and opposite force. That doesn't mean the forces cancel out because they're applied to different objects. So the general idea is that, if I push on someone, they're pushing back on me, we get pushed apart. If I pull on something, it's pulling towards me, we get pulled together. And then they'll often have different accelerations because they can have different masses. So when I walk around the room, while I am applying a force to the earth with my feet, the earth doesn't appear to move because the earth is so much more massive than me. But if you have two things of about the same mass interacting, they'll have similar accelerations. So an example of this is right here. Hopefully work. Nope, that's got a hole in it. That's okay, I have more. So here, the balloon is going to apply some force to the air in the balloon, blowing it out the back of the balloon. That will apply a force to the balloon in the opposite direction, as you can see. That's how jet propulsion works. So that's how airplanes fly. That's how boats move. They push water back, which pushes them forward. That's how cars work. They push back against the ground, which pushes them forward. Additionally, gravity. If you jump from a table, you'll accelerate towards the earth. The earth will actually also accelerate towards you, but it will be an infinitesimal amount. You won't be able to see it because the earth has a mass that's, I can't remember. That's well over 20 orders of magnitude bigger than you. So you're just not going to see the earth. So you have a small mass, so you have a big acceleration. The earth has a huge mass, so you'll have basically no acceleration. But the acceleration of the earth, the acceleration of you will actually, if you multiply by the masses, mass n times acceleration 1 will equal minus mass 2 times acceleration 2. So when you drop something, the earth is pulled upwards. Not a lot, in fact, a very small amount, but it is pulled upwards. And you experience Newton's laws in action whenever you ride in a car. Friction on the tires. If you're in a car going around a corner, the necessary centripetal acceleration to move you around the corner is provided by friction from the tires. Passengers will continue straight ahead in their original direction as the car turns and the door comes towards the passenger. That's why you feel like you're flung outwards when you turn a corner. That's Newton's first law. And Newton's third law is that the car, eventually you run into something in the car like the door or your seatbelt or whatever, and that pushes against you. That's Newton's third law. You push against it, it pushes against you. So if I apply 21 newtons of force downwards on a table top, what force does it apply to me? 21 newtons up in the opposite direction. Oops, that was wrong key. Force of 1 on 2 equals minus force of 2 on 1. Force of the table on the human equals minus the force of the table of the human on the table. Minus 21 newtons down, or minus 21 newtons, is 21 newtons up. 21 newtons in the opposite direction. Here, we have two masses connected with a spring. Mass 1, a 1 kilogram mass, applies a force on mass 2, a 2 kilogram mass, that causes mass 2 to accelerate away at 1 meter per second to the left. You can think of that as negative 1 meter per second squared. So what force does mass 2 apply to mass 1? And what acceleration does mass 1 achieve? So mass 1 is applying a force on mass 2. So this is a 2 kilogram mass is accelerated at 1 meters per second squared in the negative direction. So we want to find what the force on mass 1 is and what acceleration mass 1 achieves. Mass 1 is 1 kilogram. So remember, force equals mass times acceleration. And Newton's second law, in this case, will give us force 1 equals minus force 2. And you should be able to do. And for the last part, you can actually use mass 1, acceleration 1 equals minus mass 2, acceleration 2. Times. So it'd be negative 2, and then you do negative. That would be this F2. The negative F2 will give you F1. So the force on mass 1 will be 2 newtons in the positive direction. And then if you want to find the acceleration, you'll divide by the mass. So the force of 1 on 2 is mass 2 times acceleration 2. That is 2 kilograms times minus 1 meters per second squared. So it's negative 2 newtons. So the force of 1 on 2 will be minus the force of 2 on 1. The force of 2 on 1 is minus the force of 1 on 2, which is minus 2 newtons. Force of 2 on 1 is going to be 2 newtons to the right, positive. That is mass. The force of 2 on 1 is going to be mass 1 times acceleration 1. So acceleration 1 will be the force of 2 on 1 divided by mass 1, 2 newtons divided by 1 kilogram. Will give an acceleration of 2 meters per second squared to the right. So because this has double the mass, it ends up with half the acceleration. Because the forces are equal in size and opposite in direction. And if you were just looking for, acceleration 1, I wrote that poorly. Let me clean this up. If you were just looking for acceleration 1, you could do mass 1, acceleration 1 equals minus mass 2, acceleration 2. and you get the same 2 meters per second squared to the right. Forest one on. Does everyone have this? Everybody got this? Cool. So if you have a car that suddenly accelerates at 3 meters per second squared to the north, what force does the car apply to a 100-kilogram driver, and what force does the 100-kilogram driver apply to the car? No, it's going to be mass times acceleration. So yes, the car will apply 300 newtons to the north to the driver, and the driver will apply 300 newtons to the south to the car. So the force of the car on the driver is going to be the mass of the driver times the acceleration, which is 100 kilograms times 3 meters per second squared, which is 300 newtons north. And the force of the driver on the car is going to be minus that, which is negative 300 newtons or 300 newtons south. And the fact that forces come in pairs like this is why you only need to worry about external forces, because all internal forces will cancel out. Here we have a 12-kilogram mass sitting on the table at rest. What force does the table have on the mass? What force does the mass have on the table? So this, you're going to use two ideas, Newton's first law and Newton's second law. Newton's first law says this is sitting at rest and not moving, so the total force on it has to equal 0. So you can use that to figure out the force the table has on the mass. And then you can use Newton's third law to figure out the force the mass has on the table. Remember, the weight of something is going to be G times 9.8. No, because the total force is 0, but the total force is the force from the table on the mass minus the weight. That equals 0. And this is going to be the mass times G. We'll do 9.8 times 12 to find the weight. And then, as you can see here, the force of the table on the box minus the weight has to equal 0. So the force of the table on the box is going to be effectively minus the weight. So it'll be the weight pointing up. So here, the net force is the force of the table on the box minus the weight. The weight is mass times G. So the force of the table on the box ends up being mg pointing up, or 12 times 9.8, 12 kilograms times 9.8 meters per second squared up, which is 117.6 newtons, which rounds to 120 newtons, because this only has 2 sig figs. Then the force of the box on the table is going to be minus the force of the table on the box, so it's minus 117.6 newtons. So, minus 117.6 newtons, minus 120 newtons. It's 120 newtons down instead of up. Well, you have to round to 120 because it's only 2 sig figs, but it's 120 pointing down. That's why it's negative as opposed to up. So the table is pushing up on this mass. The mass is pushing down on the table. And that's all I wanted to cover for today. So any questions? Okay, then you're good to go. I'll see you all on Wednesday. Let me skip. Stop sharing.